All right, this is a video explanation on a topic called expected value for random variables. Okay, what does all that mean? Well, here's a question that gives us the reason for studying this concept. So here's a game I created called $100 for the Ace of Hearts. And here are the rules for the game. It costs $5 to play. You pick one of the cards from the deck. If you're lucky, quote lucky, and you get the Ace of Hearts, you actually win, in quotations, $100. They give you $100. If you get any of the other aces, you would, quote, win $10, and you would get $5 back from them if you got any of the other hearts that are in the deck. The question is, should you play the game or not? That depends on who you are and what your opinion is about the grand prize and how much that $5 might mean to you. Will the person that's running the game, that's giving the payoffs to the player, will they eventually lose more money or will they gain money? Is the person in the long run going to be losing money or gaining money if they play it time and time again? So there's a temptation to play the game, but is the temptation strong enough to decide that you should play or not play? To figure out the answer to this question, as a number, we calculate something called the expected value. Before we do that, what we're going to do is we're going to lay out a chart, a distribution table, that shows all the possible profits and the chance of actually winning those profits. So when you play the game, there's four things that could happen. You could either win $95. Well, I thought it said $100 for a grand prize. Well, you have to remember that you have to also pay $5 to play. So it's a $95 grand prize. Second prize is winning $5, because if you get $10 back, you've actually profited $5. You get your $5 back for any other heart. And there's a fourth possibility. You lose all your money, your negative $5 in the hole, if you do not do any of those things. For each of these probabilities, we're going to have to take a look at the deck of cards and decide. The chance of winning a grand prize is getting the Ace of Hearts. That's going to happen on average once out of every 52 draws. To get another ace that's not the Ace of Hearts, there's 3 of those, so the chance of winning that is 3 out of 52. The chance of getting any heart that's left in the deck besides the Ace of Hearts would be 12 out of 52. And that means that there's 36 cards that would be loser cards out of the 52. Now that we laid out the probabilities, maybe you're beginning to think that maybe it's not a very good idea to play this game, because the chance of winning the grand prize is really only 1 out of 52. And most of the time you're going to end up losing money or breaking even. So let's actually figure out the expected value. The expected value follows this formula. Add together each individual x times its probability. That's the way the formula is written. It's also nicknamed mu sub x. So to actually figure out the answer to this question, we're going to go to the probability table and multiply each probability times its value. So 95 times $1.50, or 95 times 1 out of 52, plus the next one in line, 5 times 3 out of 52, plus 0 times anything is 0, plus negative 5 times 3652. Once we do these calculations, we end up finding that the grand total of those numbers together is about negative 135. This represents the expected value that on each turn we can expect to lose $1.35 when we play. It's impossible to lose $1.35 each turn, but on average, in the long run, every time we play, we're losing $1.35 from our wallet. And the last thing I want to show you is how to calculate the standard deviation for a game like this. And it's a little bit difficult to explain what it is, but I'll try my best here. Question 2 is asking, how far on average are the profits away from the expected profit? The dollar value that we're looking for will represent how dramatic the prizes are with consideration to the amount of money that you have to pay to play. So let's figure out the answer first, and then I'll talk about the question, what it actually is asking, and what the answer actually means. So what the question is leading me on to believe is that we have to figure out the variance of this random variable. And that formula is a bit complicated looking. It's add together each individual x minus the expected value squared times each individual probability. Once we finish that, we'll be able to figure out the standard deviation, which is nicknamed sigma sub x, by taking the square root of the variance. So these two formulas together will get me the standard deviation of what I'm looking for. So in this question, this is what it looks like. Take each individual x, so let's start with the 95, take away the expected value, which was a negative $1.35, square it, and multiply it by its probability. Now we have to do that a total of 4 times, because we have to take each prize, take away the expected value, square it, and multiply it by its probability. What I would do is take my time with the formula. Don't be in such of a rush where you can make a small mistake. And I wouldn't try to type in the entire thing all in one shot. I would type in each individual piece one at a time. Unfortunately, on the graphing calculator, there's no speedy way to actually just type this into the calculator like as a list and then press a few buttons and boom, you get the answer. This is one that you have to actually work out by hand. So the last prize was negative $5. Take away a negative $1.35, square it, and times it by its probability, which is 36 out of 52. With all the squaring going on and the fact that these probabilities can't be negative, you always will get a positive answer for the variance. So the variance ends up being those values added together. So the first one came out to be 178.53. The second one came out to be 2.33. The third term came out to be 42.42. And the last term came out to be 9.22. So this is all done to calculate the variance, and the variance came out to be 190.5. In terms of the units, the unit measure on a variance is always the unit squared. So this is $190.5 squared, which is such a weird thing to be thinking about, is square dollars. Because the value for a variance is always, with any statistics formula, is always a squared unit, that is one of the reasons why we take the square root of the variance to calculate something called the standard deviation. So the standard deviation would be square rooting the variance. So in this case, it'd be square rooting the dollar, or the $190.5 squared. Once I do that, I end up getting about $13.80, and the squaring is gone from the unit. So what does this actually mean in terms of the game? and analyzing the game, it means that a typical prize is usually $13.80 away from the expected value. So negative $1.35 plus or minus that $13.80 would give you a typical prize range for the game. With a situation where there's only 4 possibilities, the standard deviation maybe is a little less exciting to use, but it still can be used. I mean, if it was a more complicated situation, the standard deviation might actually communicate a little bit more to us. As far as my opinion goes, in terms of how it could actually help you gauge this game and explore what the game actually means, I would say that because it's $13.80 for the standard deviation, that's giving me a measure of how dramatic the prizes are. So a bigger standard deviation in a game might mean that would mean that the prizes are more spread out, and a smaller standard deviation would mean that the prizes are more clumped together. All right, so hopefully this short video here kind of cleared up the basics of figuring out expected value and standard deviation. Again, the biggest thing here I think is you don't have to memorize the formulas, but you just have to be patient in using them. One last bit of advice is that many students will actually get this answer, but forget that they have to square root at the end to actually come up with the final answer. And it happens to teachers too. We get so busy calculating this that we lose focus on what the main goal is to actually get it down to a standard deviation. So just remember to square root at the end once you've calculated the variance. All right, and thanks for watching. Hopefully it was a very helpful way to clear up or to remind you about the most important things.